fact that they're fiber knots. And they also admit the geometry, which is often like this. And this is sort of a weird phenomenon that the same manifold can admit two geometries. I don't think that happens for closed ring manifolds. I don't know. Oh yeah, so I think like if you want to have a geometry, you should have like the GSG composition should be empty.
Yeah, but it says it composes.
Yeah, then those pieces will each admit, I guess. I don't know. So fiber space is Does anyone have any questions? You guys been doing exercises? Yeah, just down right there.
Wait 7 seconds.
That's what Malcolm tells us they're doing. Oh, wait, oh, I thought you were referring to the video.
Wait 7 seconds for their answer.
Yeah, I decided I didn't want an answer. Yeah.
But you're live.
Okay. All right, so maybe we'll start. We will have to close those doors. Okay, so I think the first thing I want to do today is go over the proof of one of the exercises that I listed last time that you guys all attempted to do outside of class. Okay, so the theorem that I want to prove is that we do not admit no non-trivial companions. In other words, if P of K equals U, then K equals U. I guess would be another way to say that. If I form a satellite knot and I get the unknot, then I must have formed a satellite of the unknot. And I guess moreover, we could then also make assumptions about it. The point here is that the companion knot has to be unknotted. Okay. Does that make sense? You know, some of the lingo is a little could be a little unclear. Okay. So we'll go ahead and suppose that we've taken some pattern of a non-trivial knot and gotten the unknot. Okay, is non-trivial, so there's not too many U's hanging around here. Okay, so the way to think about this is we've got this solid torus. We've taken some neighborhood of some knot K, which is non-trivial, and we've embedded in it some pattern P. There's some pattern in here. I won't draw it exactly, but sitting inside here, some pattern, and then the total space of this knot in S3 is U. Okay, and what we want to do is show that this is a knot itself. Okay, so let's we'll let B equal the neighborhood of K, and we'll let T be the torus boundary of the solid torus. Okay, so kind of shown here is T, I guess, in white. And then then the thing that we're going to use, the way we're going to use the fact that we're dealing with the unknot is, since U is unknotted, let's see. Well, I'll keep it with the way I did it in minutes. There is a two-sphere S with U sitting on S. So let's make that two-sphere red. So there's some sort of embedding of this red two-sphere S into S3, and we have lying on S our unknown. So the thing I was pondering was whether just to use half of S, which would be the hypothesis that U bounds a disk, and we could just use one of these halves. But we'll just we'll do it this way, since in more general cases we'll actually want to use a sphere. Okay. So if we assume that T and S intersect transversely, then what we get is that T intersect S is an embedded collection of simple closed curves lying on both of these guys, right? So one way we can draw that is we can draw the intersection of S with T on S here. So we get a bunch of loops, and I guess there's some over here. Maybe something like that. Bunch of simple closed curves of intersections. So this would be T intersect S. So generically, two surfaces in a three-manifold will intersect in a one-manifold, and since everything's closed, we get curves. Okay. So notice that if T intersect S were empty, then what would we have? T intersect, well, what do you guys think? If T intersect S were empty, what would we want to conclude?
And the sphere would be inside that solid torus.
Yeah, exactly. Then S is actually contained in the interior of the solid torus V. And then what?
But V is a neighbor. Oh no, V is neighbored.
Yeah.
You mean U? Oh, I'm sorry. No.
I guess
It was Jason, not me.
it have to be contained in a ball.
Yeah, exactly. So, we'd be inside V here, and our red sphere would be sort of somewhere in there. But more, even without too much regard to how the sphere is lying in there, what we know is that our unknot would be lying on a sphere inside V. So this would imply that P inside V is unknotted. Okay, so I guess that would somehow fall under the guise of a trivial satellite. Okay, does that make sense? So, all right, so all we've argued is that this intersection is non-empty. Okay. So T intersect S is not empty. So what we want to do is we want to choose a curve gamma in S intersect T such that gamma is innermost on S. Okay. So what does that look like? Well, we come over here to S. We've got a bunch of embedded curves on a sphere. so there's going to be at least one which bounds a disk. So maybe I'm thinking of something like this guy. So this is going to be my gamma. That's probably visible in the camera. So what does innermost mean? Innermost means there exists a disk D lying in S such that the boundary of D is gamma and D, the interior of D intersect T is empty. So maybe I'll redraw this. So somewhere here on S, maybe now I've moved U around. Somewhere in here we have some innermost curve gamma, and it bounds a disk D, which does not contain any of the other intersections between S and T. So gamma is part of that intersection, but the interior disk isn't. Okay, and just note that at least two such disks exist. So we assume that D intersect U is also empty, right? So we don't want to pick an innermost disk that contains U. We want the disk also to be disjunctive. Okay. Okay, any questions so far on the setup? Okay, so there are a couple of cases. So the first case is that gamma bounds a disk D prime, which lies in T. Okay, so what does this picture look like? So the picture here is that we have our piece of S and our curve gamma here, bounding this disk D. And then we have a piece of T sort of crashing through S. And this is T. And the curve gamma bounds a disk which is embedded in T. Okay. So now note, if we want to keep this picture looking as good as possible, we need to remember that even though the disk D didn't have any intersections with T besides its boundary, the disk D prime might have other intersections with S. Okay, so the way we're going to deal with this is we're going to use this shown place there. So the union, I shouldn't keep changing notes. So if we take the union of the disks along gamma, we get Q, which is a two-sphere in S3, right? So by the Schoenflies theorem, there exist three balls, B and B prime, say, such that S3 is B union along Q, B prime. Okay, so there's a three ball inside and there's a three ball outside of this sphere. Okay. So without loss of generality, we assume, so because Q separates S3 into two pieces, and Q, and so let's just note that Q intersect U is empty. So that means that U has to be to one side of Q or the other. So assume that U actually lies in B prime. Okay. So then what we're going to do is we're going to use B. We're going to use the three ball B use B to isotope D prime to coincide with D. Okay, so the idea here is, you have to be a little careful when you do this because the ball we're interested in B, it could be on the outside of sort of the obvious thing I've drawn. It may be that, well, actually, maybe in this case it has to be inside because use, no, because the red sphere comes in here. So it could be that U is sort of in there. But let's just, the outside looks the same as the inside. So what we're going to do is we're going to use this 3-ball to sort of isotope the northern. So you can think of D prime as like the northern hemisphere of the 3-ball, the Earth, and D is the southern hemisphere. We're going to push the northern hemisphere through the Earth until it coincides with the southern hemisphere. We can do this rel equator. Okay. And then we're actually going, that part's sort of, you can kind of describe it that way. So we used to have sort of gamma and this D, and we actually take it a step further and we sort of push it. We sort of push it off of S. So after we isotope D prime to lie in S right here, then push it clean through. Okay. And so this reduces the count of, this reduces the count of S intersect T. And so inductively, we can assume no intersections gamma of this type exist. So assume S intersect T contains no such curves gamma. Okay. And what type of curve gamma is it? Well, it's a curve gamma which bounds a disk on the torus. So maybe I'll just mention in passing that there's sort of another way to complete this step, which is to use the disk D. So maybe I'll put this in parentheses. Alternatively, we can serger T using the disk D. Okay. So what that means is we essentially remove a neighborhood of gamma from T, and we add in 2 copies of D, one above and one below. In this case, we'd be left with a torus, this one that I ended up with, union on a 2-sphere here, which bounded a 3-ball to the inside. And so we can throw away that 2-sphere and we have a new torus. So the way I did it, I like a little bit better because what we really did is we isotoped the torus. But actually, that's not always possible when you're doing these sorts of innermost curve arguments. Okay, cool. Any questions about that? All right. Okay, so case 2 is that, so again, we're sticking with our innermost curve, but now we know that it doesn't bound to T. So suppose gamma bounds a disk D prime, D prime inside V. By the way, I've used this word properly that, well, it's an embedding where the preimage of the boundary is the boundary of, so in other words, it's an embedding where the boundary is mapped to the boundary.
You usually think of transverse to the boundary too, or is that not?
Yeah, probably.
I never am sure. There's this point set topology definition of proper.
Oh, well, that's probably one piece.
Which, well, I think it sort of.
I mean, generally everything should be
I forget what point set topology means.
Preimage of compact is compact.
All right, so that may turn out for manifolds, compact manifolds with boundary, that may,
If you're assuming everything's black.
yeah, I'm not sure.
Okay. All right, so, well, if this is the case, then sort of by definition, D prime is a meridional disk for V, or alternatively for K. So if we come back to our original picture, this is the case 2 picture. Well, what do we see? We see this gamma, this which comes. We see this blue gamma bounding a disk D prime inside the solid torus. But notice that U is still disjoint from how is U disjoint from U?
Well, U is in, oh, wait.
Sorry. So I don't think I actually want to be precise. I think, now I'm worried that I maybe messed something up on my notes, but I think what I want to say is that case 2 is that D, the disk D, innermost disk, D is a properly embedded disk. That's the first case. So, and then if we just want to skip ahead, just for completeness, to see what all the other cases, that D is a properly embedded disk in the closure of S3 minus D. So D itself, this innermost disk on the sphere S, is actually properly embedded. Okay.
You're saying it's on one side or the other.
It's on one side or the other. Yeah, actually, so and a question you could ask yourself is, why does it have, well, okay, maybe we'll table that first one. But since D is disjoint from U, well, so this implies that D is a meridional disk. Meridional disk for V, and since D intersect U is empty, this implies that P has wrapping number. Wrapping number 0. Okay, that's another contradiction. Okay, and then the last case is that D is properly embedded this complement. So this implies that gamma is a longitude for, I guess, for the pattern or the companion on K. Now, why is that true? Well, gamma is null homologous in S3 minus D because, well, it's actually null homotopic, so it's definitely null homologous, which means its boundary is by definition a longitude for the knot. But I mean, but this implies then that K itself is the boundary of the disk D, or a closely associated disk D. We can extend D to the core K of the solid torus D. Okay. And so this implies that this is another contradiction, implying that the companion is is trivial. So that's a complete proof. You might wonder why gamma couldn't lie on the torus as some other slope, some other PQ curve. But the fact that gamma is sort of zero framed with respect to the torus, in other words, it bounds a properly embedded disk with respect to the torus, that's enough to tell you that it's zero frame, which means it's either the radius or the longitude. That's maybe a more complicated way of saying, of deriving the fact that stuff that we just derived that. Okay, cool. So any questions about that? This is a sort of like a standard innermost three manifold. You get a lot of mileage out of arguments like this, as we'll see going forward. So what's a corollary to this result about the unknown?
Looking at a contrapositive.
No.
Not sure.
I guess, well, it's not so bad. That's right. So I guess I'm thinking of the fact that a particular type of, I guess, well, it's not so bad. That's right. So I guess I'm thinking of the fact that a particular type of satellite construction is the connected sum. Right, so I mentioned last class how the connected sum is a special case of a wrapping number one. So this result says the unknot is not a wrapping number one pattern of any non-trivial knot. Right, so in particular, if the unknot can be expressed as K1 connect sum K2, then K1 equals K2 is unknotted. So the unknot is, well, still not prime, but something like that. Okay. And so last time I mentioned a couple other exercises that I would, encourage you guys to kind of cut your teeth on. Namely, you can use a very similar sort of thing to show that torus knots are prime or rational knots are prime. Or the other one I wrote was a proper satellite. What was it? A proper satellite is prime? Yeah, a proper satellite is prime if and only if P of U is prime. P of K is prime if only P of U. Okay. Cool. How many people had seen something like that before? Okay, good. Okay, so I think what I'm going to do now is just talk really quickly about what a Morse function is, and hopefully not spend too much time on it, and hopefully not say anything that's wrong. And then we can move on to just considering very simple examples of Morse functions. A Morse function on a smooth N manifold M is, and you guys all have taken Morse theory, so you can point out anything that is not quite right about this. So it's a smooth map to the real numbers, such that, actually, very critical point, P in M is exists a chart U containing P, or a chart x1 through xn on a neighborhood U of P such that x of I of P is 0 and f of x equals P minus x1 squared minus xk. Let's put it down here. So x equals minus x1 squared minus xk squared plus xk plus 1 squared minus coordinates on each critical point so that it has a description of this form. And the value k is called the index of the critical point. Okay. And I think I'll just collect some theorems here. I suppose these are all, these are just standard theorems from the theorem. So the first is that Morse functions are generic among smooth functions of this type, meaning that by a slight perturbation, we can always assume that a smooth function is Morse. And the second fact that I want to collect is if there are no critical points in some interval AB in R, then F inverse of the interval is a product. It's diffeomorphic to F inverse of just a point A cross I. And then if an interval of this sort AB contains a single critical point, say P, or say, I guess, contains a critical value C, then F inverse of the interval is diffeomorphic to F inverse of F inverse of A across an interval union. Hopefully you can see this, a handle. So I will write the handle HK. Where HK, which happens to be diffeomorphic to an n-dimensional ball, is an n-dimensional handle. I'm not going to talk about what handles are at this point. So this is, I don't know, it's kind of neither here nor there for us. But we're going to fix a Morse function H from the 3-sphere to R with exactly 2 critical points. Okay. And which we assume to be the poles. Plus or minus infinity. Here the way I'm thinking about S3 Or any sphere really. It's just, yeah. In fact, let's go with, will that be a problem? Let's go with S3, but keep in mind that we'll do the exact same thing when we arrive at S4. So the poles I think of as, I'll just label with infinity and minus infinity. These will be points we tend to avoid. And then all of these level spheres, so these are H inverse of some point T, are going to be diffeomorphic to two spheres. Okay. So we're really thinking of, I was going to do something funny here. Yeah, I don't know if this is, I don't know if this is standard, but let's suppose H of S3. So what is the image of H and R? Well, it can kind of be whatever we want. Let's suppose it's negative 10, 10. What I really want to do is I want to consider, I want to post-compose. I want H to go from S3 to, I guess, negative 10, 10 inside R. And then I want to send this to negative infinity union R union infinity. So I want to be able to essentially pull back and realize this is, do people do this? I don't know, it's kind of weird. But so then basically how I want to think about my.
I mean, it's a little bit like the sweep out where you start.
It's kind of like a sweep out, yeah. Yeah.
Like open product.
Right, exactly, which is the next thing I was going to write, which is that so I'm sort of thinking of S3 as the south pole, and then union the two sphere cross R, and then union the north pole. So I have all these two spheres that sort of converge towards the poles. Okay, and these are called level two spheres. Or level, let's just call it level sphere. And like I said, in general, we'll do this with the ends, with the four sphere also, in which case these things will be level three sphere cross section. Okay. So the next fact that I want is that for any compact submanifold, here I go back to M. So if we take a compact submanifold in M, you can assume that the restriction H to N from N to R is also Morse. Okay. So there's probably some details to consider here, depending on whether N is properly embedded, whether if M has boundary. Usually we restrict the boundary of M to be a level set, and we would similarly do the same with N, but we're not going to belabor those details. It should be pretty clear from each context what kind of a Morse function on N we're exactly getting. So let's just look at some examples. So we finished last time, but I gave you an example of how we can restrict a Morse function in S3 to a knot.
Question.
Yes, please.
When you say H, are you talking about this composed map or
Oh, I called the other one F. That's right. So this, I guess, was harkening back to F. Thank you. I think I was trying to make a more general statement here when I was just talking about Morse functions on M, because M came back here. Was it M before?
So the range is still in like minus 10, 10.
Oh yeah. Well, no. So the range of the restriction could be different.
It'll be a subset of that.
It'll be a subset of negative 10, 10, which I've not plugged with this. So it'll be some subset of that. That's right. Okay. I mean, and in general, it'll definitely be like a proper subset. Well, anyway. Right. Okay, so the thing we can do, for example, with with a knot in 3 space is, well, we can just massage it only slightly to assume something like this. I ran out of room a little bit. Okay. So what am I even doing here? So I've drawn the knot suggestively so that if we think of the standard height function on S3, when we're talking about serious, I don't know if we'll be too. Similarly, to a knot, if we have an embedded surface in 3 wheels, there is more sort of more interesting critical points. So these are going to be saddles. So index 1 critical points now are, I think there's a, and
2 more saddles.
oh. Thank you. And then we get some minima. So there should be some favorable canceling. Okay. So just the existence of putting a surface in a position like this is actually fairly enlightening. So you can prove, maybe I'll just say some things that you can prove. So maybe these are sort of like exercises. Okay. The first is that every closed surface in S3 is compressible. And the reason it's an exercise is because I don't think I'm going to define compressible. Compressible essentially, well, you remember in this, compressible essentially means you can find a curve on the surface, which is essential, meaning that it's homotopically essential on the surface. And there's a disk outside of missing the surface that you could serger the surface along to make it simpler. And there's a formal definition, but anyway, just by putting a surface in a position like this, you can get this fact that every surface in S3 is compressible. And then I'll in the vein of even saying more things that I'm not defining. Another thing you could, so this is just a fun exercise. So for those of you who know what compressible means, you can also think about, well, can I sort of maximally compress my surface so that it bounds what's called a handle body? Okay. Well, I'm not going to define what a handle body is yet, although they'll end up being pretty important at some point. But for now, what I'll just give for people who are interested in doing this is find a surface in S3 that bounds no handle body. Bounds no handle body. Yeah. Good. And then maybe the third exercise is proof Schoenfeld. This is maybe a little misleading. The proof of Schoenfeld's theorem uses part 1, but part 2 is not related. Okay. So those are maybe exercises for people who have advanced knowledge or want an extra challenge or something. Okay, so last time I gave the definition, which is that a link L in S3 is in B bridge position if H restricted to L is Morse with B maxima, all of which lie above the B minima. This is in parentheses, the minimum.
Okay.
So the example I drew over here is not an example of a link in bridge position because we have this maxima clearly lying below that minimum. Okay. But if we pulled that maxima up, we just sort of attached a string to it and pulled it up, then we would be in bridge position. And so that's a proof of the fact, this proposition, which is that every link can be put in B bridge position for some B unnatural number. And the proof of this is essentially starting at each maxima, find an embedded arc connecting the maxima with the point at infinity that misses your knot, which you can do generically by codimension count, and just pull it up. All right, and okay, I think I just want to state one theorem, which I was maybe going to prove, but I might not now. And I sort of gave a proof of it in the notes, in the handwritten notes. So I might just refer you there, but it's at least worth stating. So this is famous theorem/theorems of Schubert from 1954. Okay. So this is when the notion of a bridge position was first invented. And Schubert proved that, oh, I should define the bridge number. Okay. The bridge number of L is B of L, and it's the minimum number of maxima required to put L in bridge position. Okay. And what Schubert proved is a couple of things. He proved that the bridge number of the PQ torus knot is the minimum of P and Q. He proved that if K is a connected sum, then the bridge number of K is the bridge number of K1 plus the bridge number of K2 minus 1. And he proved that if K is a satellite knot with pattern P and companion J, then bridge number of K is greater than or equal to little k times the bridge number of J, where K is the wrapping number of P. Okay, so the cool thing about all of these results is that they're pretty accessible to prove and very hands-on. And in fact, all the reference for this, I think, is not Schubert, but oh gosh, I guess it doesn't have a C, does it?
It does have a C.
It does. Okay. It's that thing at the board, you know, your IQ just like plummets. Mine doesn't have far to go, so. Okay, so I think a good reference for understanding these proofs is two papers that Schultens wrote using sort of modern techniques. To read Schubert, you need to understand like old math and German. So that's two barriers. But Schultens has two really nice write-ups, and I sort of recreated one of them in the notes. So the general idea is these knots, as I've mentioned, come with these ancillary surfaces, right? The torus it lies on, the reducing sphere, the companion torus. And the idea is to put that ancillary surface in Morse position and start canceling critical points in a very controlled way. And you can prove these kind of cool things. All right, so next time we will start talking about bridge splittings in earnest. And great, thanks. See you on Monday.